Okay, so for today lecture, we still in the chapter 1, okay, but we go for the details on the elements lah. Okay, so we still in chapter 1, introduction to vibrations. So now we on a week 3 lah, week 3, and then this is the aspect outcomes lah for this chapter. So try to finish this chapter within this week lah. Okay, so which is first outcomes, identify the different type of element of vibrations, identify the different type of vibrations, analyze the series and parallel stiffness and damping elements. Okay, so basically the last week lecture we go about how to model the vibration system. Okay, so which is consists of the mass elements, spring element and damping elements. So for this week lecture, which is the slide for lecture 2, we go details on each elements lah, especially for the spring and damper. Okay, for the first part, we go for the first. This is elements for the vibration system. Okay, so which is a model as spring elements, mass element, and damping elements. So basically, spring element is relates with the potential energy. Okay, so which is if we present in the unit of force, you can consider as F equal to Kx. And mass elements, which is the initial, so relate with the initial force, F equal to ma. And then the last one is damping, is about the energy dissipation. Okay, so which is F equal to C, which is damping coefficient, times by velocity. So this force for the spring element is relative to displacement. So if no displacement, so mean that there is no force. Same goes for the mass elements. Okay, so if there is a accelerations, so mean that there is a inertia. Okay, if move with the constant velocity, meaning that there is no inertia, initial force. And the last one is damping. So damping is relative to velocity. Okay, so this is the symbols symbol used for the translational elements so which is for if we model the system with the translation motions, so either it move vertical or horizontal, then this is the normally symbols so stiffness, spring, so use the symbol. Okay, and sometimes okay, so sometimes we use this kind of symbol. Okay, so normally we use as a K K or S. Okay, so the commonly used in the textbook. And this is mass. So mass symbol is M, and damper C damping coefficient. So this one is Newton over meter, is kg, Newton seconds over meter for the damping. And this one for the rotational element or torsional elements. So this one is relates with the rotational motion or the torsional vibration. So if you have a mass attached on the disc attached on the model using the symbols. So this one for the torsional spring. Okay, so we use KT The difference between rotational elements and the translations. For the translation, we use symbol. We develop equation based on the force applied to the system, lah. Which is total force equal to zero. Which is we summation all the forces come from the stiffness, come from the mass, and come from the damper. So it should equivalence to zero. This one for the translation. Okay, for the rotational, instead of instead of force, uh, we develop the equation of motion based on the moments or the torque. Okay, it's almost equivalence. The way we construct the everything is about equation of motion. Okay, for example, for the torsional spring, if we want to calculate the torque value, is equivalence to uh, kt times by the torque divided by the Okay, so I think we continue. Sorry, my laptop have problems. Just we restart. Okay, so we continue with the rotating elements. Okay, so as mentioned, for the translation, we develop equation of motion based on the force equivalence. So which is the summation all the forces applied to the system should equivalent to zero lah, because we consider that the system in dynamic equilibriums. Okay, and then for the rotational motion, so which is rotational motions, meaning that we measure the motion based on the angle displacement. So which is um, translation we measure using SI unit for the meter lah for the displacement. Okay, but for the rotational, um, we use the uh, angle displacement. So meaning that in invariance. Okay, so instead of force, we measure the torque applied to the system. Okay, so which is torque of moment. Okay, so for the torsional, okay, so M is equivalent to KT times theta lah. Okay, so theta is a angle displacement. Okay, and this one is inertia. Okay, so inertia, we use mass moment of inertia lah as parameters to determines the inertia, rotating inertia. Okay, so which is M for inertia is equivalent to J theta double prime. So which is which is acceleration in the rotational directions and then damper the total of the moments can be calculated based on the CT times by theta dot, which is velocity lah. So for this case, the total of the moment should be equal to zero. Okay, so this is just a symbol. Okay. Then mass moment of inertia is depend on the geometry and also the mass of the object lah. Okay. Different geometry, different equations. We detail after this for the example. Okay, so now we go for the first as a spring elements. Okay, so we look at for the linear spring lah. So because for this subject we only looking for the linear system. So we can define as a linear spring as a type of mechanical link that is generally assumed to have a negligible mass and damping lah. So this one by theoreticals lah. So because we want to consider that it only have stiffness without any mass and damping. But if you refer for the actual spring, actually inside the material inside have their own damping lah. But for this case, we just consider that there is purely have a stiffness and zero damping and zero mass lah, which is doesn't affect the spring itself. Okay, and the stiffness force is a word to bring the mass back to the position of equilibriums. Okay, so which is based on the Hooke law lah. So F equal to Kx. Okay, force equal to stiffness, spring deformation or deflection of the object. Okay, so stiffness is Newton over meter lah, the units. So for this case, make sure that if you want to do the calculations, you have to convert to the SI units. Okay, so for the displacement, you have to convert to meter. Okay, if the question given mm, the first step you have to convert lah to SI unit. So it depends. The spring element doesn't mean that the form of the spring element should be in the spring. So and any kind of the structure can be modeled as a spring lah. So for example is cantilever beam. Okay, so cantilever beam, you know that if we draw the cantilever beam something like this, okay, you fits and then uh, this is a cantilever beam. If you put mass, okay, and then mass have a motion lah. So this is the deflection of the mass in the X. So which is mass, um, the M if moving in the vertical directions. Okay, and then for this case, the resistance from is coming from the cantilever beams. Okay, so which is give the resistance in the vertical direction lah. So for this kind of motion, if you refer back to the strength of material or the static subject, okay, then is equivalence to this is static deflection, so which is the weight times by the the length, and then over 3 EI lah. So E is the properties of the cantilever beams lah. So which is Young modulus or modulus of elasticity, and then the polar moment of inertia. So which is depend on the cross section of the beam itself lah. Okay. For this one, as we know that F equal to K X, right? Then X is equivalence to static deflection lah. So F apply is equal to this one is the weight, okay, and then this one is a static deflection lah. Okay, and then so for this system, okay, so the stiffness can be modeled as a the W, which is the weight over static deflection lah. So we just modify to this this equation. Okay, so this one move to this side and other move to other side lah. Okay, and then this is what we got. So mean that if you face this system and then you want to model and you want to know that what is the equivalent stiffness for that system, then you can refer this formula lah. So based on the cantilever beam, and then this one also can be model. So if you want model to the vibration system, so this is mass and then this is stiffness. So this is the way we model the system. So and this one is K. K is a stiffness which is based on this value lah. So actually it's depend on the motion lah. Okay, so for example this one is goes to the vertical motion. If this mass move in the horizontal, and then the calculation the equation is the same, okay, but you have to consider the polar moment of inertia because there is a 1/12 based on the rectangular area lah. Okay, so BL lah, so base BH lah, base height. Okay, so this one just a refreshment. I believe all of you already learned in the strength of material or static subject. Okay, so this is how we model. So even this, there is no spring for this system, we can still model as a spring mass system lah. For this one, there is no damper. Actually, for if you model as an actual, it should be spring mass damper lah. But for this case, because this one we just go for the theoretical part, so we just ignore the damping elements lah. Okay, so first we can model as a spring mass system. So mass is depend on the the mass lah, what is the value in kg, and then the stiffness you have to consider the equivalent stiffness lah. Okay, so equivalent stiffness is actually is depend for cantilever beam itself, actually is depend on the motion, the direction of motion. So if it move in the vertical, and then there is different value for the stiffness, and it move for the horizontal, um, means have a different stiffness. Okay, then there is a few ni lah, equations for the K equivalence for beams lah. Okay, so this is for the fits. Okay, so it depend lah. So if the you have a beam with the fits, so fits meaning that you have beam here. Okay, then so this is fit lah, and then this one is simply supported. Okay, so simply supported. So so it's either have a roller here or the pin lah, pin. Uh, okay, then cantilever beam. Okay, so fits for the one of the beam end. Okay, and then this one actually the same cantilever lah, but the direction of the load lah. Okay, so if the load apply in the axial directions, so must use this equation lah. So if you have a mass on the top of this beam, and then you want to consider the vertical, and then so meaning that the force apply in the axial direction, so you can use this equation lah. So actually, even you have a cantilever beam, to determine the equivalent stiffness also is depend on the motion that you consider. Okay, so for example, this one is a beam you fit at the end of this shaft. Okay, so if you want to consider in the uh, horizontal motion, you put mass on top of it. So then you have to consider as a cantilever beam lah. So and polar moment of inertia is depend on the geometry lah. Okay, and then if you want to consider the motion in the horizontal, okay, which is horizontal, so the equivalent stiffness for this system, you can just refer for the K equivalence for the what under axial loading. Okay, and then one more thing, if you face with the if the mass is a twisted, okay, so it's a twist, that one you have to consider the torsional lah, the torsional system. So you have to consider the top. So even it's the same cantilever beam, so the equivalent stiffness is depend on the direction of motion that you consider in the calculations. So this one fit for the ni lah, middle load. Okay, same goes for the simply supported. Okay, so this one is how we define the model lah, the stiffness. What is the stiffness? Actually, everything can be defined as stiffness lah. If you give force a deflection, then you have a stiffness, and once you release, and then it back to the equilibrium position. So meaning that that system have their own stiffness lah. Okay, then it's about the combinations. Okay, so sometimes we have more than one damping, the stiffness elements, and then we have to know that how to find the equivalent stiffness for the system lah. So first we have to identify the stiffness is either in the parallel arrangement or the series arrangement. Okay, so once you identify that the arrangement for the spring, and then we can determine the equivalent stiffness. Okay, and then for example, if the spring is parallel, so meaning that all the spring is directly contact to the mass, and then we can find the equivalent stiffness based on the summation of the all the stiffness lah. Okay, so K equivalent is equal to K1 plus K2 and plus dot 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 until Kn lah, how many K. Okay, this one for the parallel. Okay, and then if a series, so series meaning that spring is connected to spring and then connected to the mass lah. For this one we consider as a series. Okay, so I think that slide we have a figure. So for the series, to find the K equivalent, which is based on the listed equation lah on the slide. So 1 over K equivalence is equal to 1 over K1 plus 1 over K2 and plus how many spring in the parallel arrangement. Okay, so this is example for the parallel, and then this one for the series. Okay, so uh, the easiest way to understand either parallel or series, for the parallel, all the spring is a directly contact to the mass, so which is the knot for this spring and the knot for this spring share the same coordinate. Okay, so that's we can consider as a parallel. Okay, for if a spring is connected to the spring, so this one we consider as a series. So for this one, it looks simple because we just use a simple spring. But sometimes if there is a combinations of which is the different type of spring, okay, then you may face the difficulties to identify. For example, okay, if we have a cantilever beam, okay, then we have a mass here, and then on top of it, we attach another spring. Okay, and then have another example. Oh, sorry. F cantilever beam, and then we put another spring here and then attach to the mass. Okay, so for the first example here, okay, so to identify, as I mentioned before, to identify either this one is a parallel or series. Parallels meaning that all the spring is a directly contact and it share the same coordinate. Okay. So if the first spring move 1 unit and then the second spring also move 1 unit. So which is this not of this one we can consider as a parallel. Okay, because the spring from the cantilever beam is contact to the this mass. Okay, and then another additional spring also is directly contact to the mass. So meaning that is a parallel. For this case, we can consider as a parallel. And then for the second example, this one, this spring is a contact to the spring, spring contact to the spring, so meaning that is a series. Okay, Okay, so for example, this one is a K beam. K beam. This one K L. So this one K beam. KS. Okay. So this one, if we want to model, so we can model as a mass. This one is a so K beam and KS. For the second example, can model like this. Okay, so this one K S K beam. Okay, so K equivalent for this one. So K equivalence equal to K beam plus KS. So for this one, K equivalence, sorry, 1 over K equivalent equal to 1 over K beam plus 1 over KS. Okay, so that's the difference for the uh, series and parallel. Okay. Okay, and then okay, so now we look at for the spring elements. If we consider the torsional, so which is a rotational motion. This one, the simple example we take as a shaft lah. Okay, so shaft. Okay, so the stiffness for the shaft in the rotational directions is equivalent to Gj over L here. Okay. So which is G is the shear modulus. Okay, so J is based on the geometry lah. Okay, so it's a pi d power of 4 over 32 lah. So that's one for the shaft. And if we consider the hollow shaft and then the outer diameter minus the inner diameter, okay, and then same goes for the this part and this part. Okay, so this example, as mentioned before, normally there is a the disc or any mass applied in the rotational motion. So the equivalent stiffness is based on the stiffness for this part plus for stiffness for this part. First, you have to identify both of the shaft is either series or parallel. Okay, so this one KT1, this one is KT2 lah. Or for this case, KT1 is considered as a 1, 2. So which is from point 1 and point 2 and point 2 to point 3. Okay, so there is two different stiffness because the geometry is different. So which is the stiffness for this hollow shaft is not equivalent to this hollow shaft. So mean that have a different stiffness between point 1, 2 and 2 and 2, 3. So for this case, if the mass is attached at the point 3, so meaning that you have to find the equivalence, the equivalent stiffness. For the equivalent stiffness for this case, this shaft is contact to the shaft, so this spring contact to spring and then contact to the mass. So meaning that this one, the first shaft doesn't directly contact to the mass. So mean that for this case, we can consider as a parallel. Sorry, the series arrangement. So series, that's why the K equivalence 1 over K equivalent is equal to 1 over KT1 plus 1 over KT2 lah. So this is the how we determine for the ni lah stiffness lah for the torsional. Don't worry about the equations. Normally, if you ask in exam, the question will be given. So, unless you are facing the open book test, so open book test meaning that you can refer your notes lah to find all the equation. Okay, so this is for the spring element lah. But for the case that if you put the hollow bar as a side by side, so mean that like this example lah. So this is fixed. Okay, so this is hollow shaft. And then you add another hollow shaft inside that, which is two different material. So which is two different material, meaning that it have two different stiffness. So for this case, if you put this, which is have a rotational motion. So for this case, both of the shaft is directly contact to the mass, and then for this case, we can consider K equivalent equal to KT1 plus KT2 lah. So that's different between parallel and series lah. Okay, so I think this one we continue for the tomorrow session because we already reach almost 10 o'clock lah. So I think for today lecture we stop until this point. Do you have any question for the today lecture?
No, sir.
No, sir.
No, sir.
No, sir.
Okay, so thank
No,
you for
sir.
your response. I think that's all for today. Thank you for your attention. Okay, see you again tomorrow, inshallah.
Thank you, sir.